Hello everyone. Welcome back to Buttery Game Theory. Mastering Advanced Game Theory Episode 3. Solving Extensive Form Games with Subgame Perfect Nash Equilibrium. In this episode we'll learn how to represent perfect information games using game trees, how to solve them using backward induction to get the Subgame Perfect Nash Equilibrium, and lastly look at another example, where there is uncertainty in the game. Imagine you're Alice, a startup founder deciding whether to invest in a new technology. Bob, an investor, is watching your moves closely and will decide whether to fund your project only after seeing your commitment. So how's the game tree look like for this example? The game starts with Alice making the first decision, represented with the initial node. She has two possible actions, either to invest or not, so there are two branches following this node. At the end of these branches we have non-terminal nodes for Bob. Whatever the decision Alice made, Bob will then decide whether to fund or not. So there are two branches from each of these nodes. At the end of each branch there is a terminal node, where we assign the payoffs. Since there are two players, there are two elements in each payoff vector. The first belongs to the first player, Alice, and the second is for Bob. Since this is a perfect information game, we can use backward induction to solve it. First we see the last decisions to be made by Bob. For this subgame, when Alice decides to invest, Bob's best response is to fund it. Meanwhile, if Alice wasn't investing, Bob should not fund it. Knowing that Bob is a rational player, Alice knows what Bob's best responses are, and hence she will choose her best response depending on Bob's best response. So her best response is to invest. Now to find the subgame perfect Nash equilibrium, we just follow the arrow from the initial node to the end terminal node. And this is our subgame perfect Nash equilibrium outcome. And the strategy profile that leads to this subgame perfect Nash equilibrium is I-F-N. There is one strategy for Alice and two for Bob, respective to the number of the decision nodes they have. If we want to draw a payoff matrix from this extensive form, we need to list all possible strategies from player 1 on the y-axis, and the strategies from the player 2 on the x-axis, and map the payoffs for each of the strategy combinations. To get to this payoff, we look at Alice's and Bob's strategies. The first row is when Alice invested. For Bob we only need the first part of the strategy set, since that is the corresponding strategy for when Alice invested. Meanwhile, when Alice did not invest, we look at the second strategy from Bob to determine the payoff for the second row. And that's how we get our payoff matrix. Now, let's take a look at a slightly different game where Bob does not know if Alice invested in it. The graph will now look like this. So what does this mean for us? Our second player, Bob, is now uncertain about his position in this game, whether he is in this node or that node. Instead of two information sets and two decision nodes just like in the previous example, here, he only has one information set and one decision to make. So how can Bob make the best informed decision in this imperfect game? Let's look from Bob's perspective. If he decides to fund it, he might get 2, but he might also get 0. When he decides to not fund it, he will get 1 for sure. Based on this observation, there is no clear difference in the total payoff he might get by choosing one or the other strategy. But then Bob remembers that Alice is a rational player, so she will choose the best strategy for herself. Knowing that, he calculates the possible payoffs for Alice. If Alice invests, she might get 3 or 0, meanwhile when she does not invest, she'll get either 4 or 2. Whatever Bob will choose, Alice is better of choosing not to invest. So knowing this, Bob's best response to Alice's strategy is not to fund it. To see if this is in fact the only SPNE in this game, let's look at the payoff matrix. Since Alice and Bob only have one decision node, both only have one set of strategy. And then map the payoff respectively. Here we see that the normal form reflects the standard simultaneous game, that is because each player does not know what the other player is going to decide. Now we just need to look for the best response for Alice and Bob, and the ones who have both best responses are our Nash equilibrium. And since in this game there is no other subgame other than the game itself, the subgame perfect Nash equilibrium is the same as Nash equilibrium. But you can see that in our previous example, it was not the case. The Nash equilibrium is not the SPNE in our first example. So that's it for today's episode. In the next episode we will learn how to solve sequential games with incomplete and imperfect information using perfect Bayesian equilibrium. Thank you so much for watching. Till then.